Imagine a world where energy flows effortlessly, powering our homes and vehicles with unprecedented efficiency. This is the promise of proton conduction, a fascinating phenomenon at the heart of fuel cells and other clean energy technologies. At the forefront of this revolution are metal organic frameworks, or MOFs, a new class of materials with extraordinary properties. MOFs are like intricate Lego structures built from metal ions and organic linkers. These building blocks can be assembled in countless ways, creating a vast library of materials with tailored properties. One of the most exciting applications of MOFs is in proton conduction, where they act as superhighways for protons, the tiny charged particles that carry electricity. But not all MOFs are created equal when it comes to proton conduction. Join me as we unlock the secrets of these materials and discover their potential to revolutionize energy storage and fuel cell technology. Hydrophilic MOFs are like sponges, eagerly soaking up water molecules from their surroundings. This affinity for water arises from the presence of polar groups within their structures, which attract the positively and negatively charged ends of water molecules. As water molecules infiltrate the porous network of hydrophilic MOFs, they create a labyrinthine system of interconnected channels. These water-filled channels act as conduits for proton transport, enabling the efficient movement of protons through the material. The presence of water is crucial for proton conduction in hydrophilic MOFs. It facilitates a process known as the Grothus mechanism, where protons hop from one water molecule to another, like a molecular relay race. At low humidity, when water is scarce, proton conductivity is limited. However, as humidity increases, more water molecules fill the pores, creating a denser network of proton highways. One remarkable example of a hydrophilic MOF with exceptional proton conductivity is MIT-25. MIT-25 stands out in the crowded field of MOFs as a true champion of proton conduction. Its secret lies in its unique porous structure, a masterpiece of molecular architecture that optimizes water uptake and proton transport. Unlike many other MOFs which have a single type of pore, MIT-25 possesses a hierarchical pore system with two distinct pore sizes. The larger pores, measuring about 1.1 nanometers in diameter, act as reservoirs, readily absorbing water molecules from the surrounding environment. These water molecules then diffuse into the smaller pores, which are only 0.6 nanometers wide, creating a dense network of confined water channels. This confinement of water molecules within the narrow pores of MIT-25 has a profound impact on proton conductivity. The close proximity of water molecules enhances their interaction, facilitating the rapid hopping of protons through the Grothus mechanism. As a result of its unique structure, MIT-25 exhibits exceptionally high proton conductivity, particularly at high humidity levels. In the next section, we will shift our attention to hydrophobic MOFs, which exhibit a completely different behavior towards water. Section 4, Hydrophobic MOFs, Proton Conduction in Water-Repellent Environments. Hydrophobic MOFs, in stark contrast to their water-loving counterparts, exhibit a strong aversion to water. Their pores are lined with non-polar groups that repel water molecules, preventing them from entering. This water-repelling nature might lead one to believe that hydrophobic MOFs are poor conductors of protons. While it is true that bulk water plays a crucial role in proton conduction in hydrophilic MOFs, recent research has revealed a surprising phenomenon. Proton conduction can occur even in the absence of bulk water, within the confined spaces of hydrophobic nanochannels. Imagine a narrow, water-repellent tube. If we introduced just a few water molecules into the tube, they would behave quite differently. These confined water molecules would interact strongly with each other and with the walls of the tube, forming a thin film or a chain of water molecules. This is precisely what happens in hydrophobic MOFs. These confined water molecules exhibit unusual properties, forming strong hydrogen bonds with each other and with the MOF framework. These strong hydrogen bonds create a pathway for proton conduction, even in the absence of bulk water. Section 5, MONs, Unveiling the Secrets of Hydrophobic Proton Conduction. Among the many hydrophobic MOFs that have been synthesized, one particular family stands out for its remarkable proton conductivity, the MONs, short for metal organic nanotubes. These MOFs possess one-dimensional channels that are lined with hydrophobic groups, creating a water-repellent environment. Despite their hydrophobic nature, MOFs have been shown to exhibit surprisingly high proton conductivity, even at low humidity levels. One of the key factors contributing to the high proton conductivity of MOFs is the size and shape of their nanochannels. The channels are just the right size to accommodate a single file of water molecules, creating a confined environment that enhances proton transport. This chain of water molecules acts as a proton wire, facilitating the rapid movement of protons through the material. The discovery of proton conduction in hydrophobic MOFs like MOFs has opened up new avenues for designing proton-conducting materials. Section 6. Applications, powering the future with MOFs. The unique properties of MOFs, both hydrophilic and hydrophobic, have positioned them as front-runners in the quest for clean and efficient energy technologies. Their ability to efficiently transport protons, coupled with their high surface area and tunable pore sizes, makes them ideal candidates for a wide range of applications. One of the most promising applications of MOFs is in proton exchange membrane fuel cells, or PEMFCs. These fuel cells rely on a proton-conducting membrane to separate the anode and cathode, allowing protons to flow from the anode to the cathode while preventing electrons from doing the same. Traditional PEMFCs use expensive and complex materials like naphthalene as the proton-conducting membrane. MOFs offer a potentially cheaper and more efficient alternative. Their high proton conductivity, especially at elevated temperatures, could significantly improve the performance and durability of PMFCs. Beyond energy storage, MOFs are also being explored for their potential in gas separation, catalysis, and sensing. Section 7. Conclusion. A glimpse into the future of proton conduction. As we peer into the future of proton conduction, metal-organic frameworks stand out as beacons of hope, illuminating a path toward a cleaner and more sustainable energy future. Their unique ability to transport protons efficiently, coupled with their tunable properties and diverse structures, has positioned them at the forefront of materials science research. Hydrophilic MOFs, with their love for water, have demonstrated exceptional proton conductivity, particularly in humid environments. MIT-25, with its intricate pore system, exemplifies the potential of these materials to revolutionize fuel cell technology. On the other hand, hydrophobic MOFs like the intriguing MOFs have challenged our understanding of proton conduction by demonstrating that efficient proton transport can occur even in water-repellent environments. The journey of MOFs has just begun, and the future holds immense promise. From more efficient fuel cells to advanced energy storage solutions, MOFs are poised to play a pivotal role in shaping a brighter and more sustainable future.